last talk for this block. I wonder if the tram ding is the same one as last year's. Apparently it was the wrong ding for the tram on the PyCon AU logo last year, so trust a conference full of PyCon devs to have a slightly unhealthy obsession with trams. For our last speaker for this block, we have Russell, who is going to be talking about taking wheels mobile. This looks really interesting because I always thought wheels were mobile. So give him the classic, big, warm PyCon AU welcome, and I'll hand it over to Russell.
Well, hi there. My name is RussellKeith-Magee. I am here today to show you how you can generate binary wheels in Python, and more specifically, how to generate binary wheels for mobile platforms like iOS and Android. First off, who am I? I am from Majuk Nungabuja, otherwise known as Perth, Western Australia. I'm a member of the CPython core team. I am the principal engineer in the open source group at Anaconda. Anaconda pays for me to attend conferences like this one, to talk to people like you, so I'd like to thank them for that support. They also support the Python open source ecosystem more broadly by providing direct financial support to organizations like NumFocus and by employing developers to work full-time on open source projects like Jupyter and Number, and the open source project that I founded, Beware. For those who haven't come across it before, Beware is a collection of open source tools and libraries for creating native user interfaces in Python for desktop, but also for iOS, for Android, for single-page web apps, and for console. But today, I'm not going to be talking about Beware, at least not directly. For the last 10 months or so, my co-worker Malcolm Smith and I have been working on the tools in the broader Python packaging ecosystem, adding support for iOS and Android. This work is not part of Beware itself. Beware uses these tools, but since iOS and Android are now officially Tier 3 supported platforms for CPython, any other project that wants to target iOS or Android can also use these tools. So today, I'm going to be talking about that work, about wheels, how you build them, and more specifically, how you build them for iOS and Android. So, what even is a wheel? Well, a wheel is the redistributable unit of code in the Python ecosystem. It was standardized in PEP 427. It's not a complex instrument. It is basically a zip file containing Python code in the installed directory layout, along with some metadata describing the package and optionally some actual data for the package to use. The contents of the wheel is designed so that it can be unpacked directly into to a location on your Python path, usually cite packages, but not necessarily, and then used without the need to run any additional Python code or run a compiler or anything like that. The wheel itself has to follow a very specific naming pattern. What's in a name? Well, an identifier for the package version, and then the platform applicability of the wheel. The package identifier has to adhere to PEP 508, the version number has to adhere to PEP 440, and that leaves platform applicability in 3 parts. There's a Python tag that describes which Python implementation the code is compatible with. Py3 for any Python 3 interpreter, CP314 for a CPython 3.14 interpreter, PP311 for a PyPy 311 interpreter, and so on. Then there's the ABI tag, the application binary interface. This describes the compatibility of any binary Python components in the wheel. This will be none if there's no binary compatibility concerns. It could also be a specific Python version that matches the Python tag, CP314. It could also describe a variant, so something like CP314T means the code requires a free-threaded build of Python. Or the wheel could declare ABI3, that it uses the stable ABI, which is a subset of the Python ABI that is guaranteed stable across Python versions. Lastly, there's the platform tag. This is where you declare operating system and architecture compatibility. This can be a single platform like Win32 or platform and architecture, WinARM64, for example. It could include a minimum version of an operating system like macOS 11. It could describe a meta architecture. Universal 2 describes a wheel that will work on macOS on both ARM64 and x86-64. Even the operating system can be a meta tag. Linux isn't an operating system by itself, it's just a kernel. So the many Linux and muscle Linux specifications describe sets of system libraries that the wheel can assume exists. As an end user, you just pip install my package. Pip then goes to PyPI, finds all the wheels that match, considering your operating system version, CPU architecture, Python version, Python variant, and builds a list of candidate wheels, including binary wheels and pure Python wheels, which can actually themselves be platform-specific if they need to be. Pip's resolver then works out which wheel is the best match and installs that wheel. But as a package developer, that means that for each release, you need to build wheels for multiple operating systems and operating system versions and meta-operating systems and architectures and meta-architectures and multiple Python implementations and versions and ABIs. Pillow, for example, is the gold standard library for image manipulation in Python. Pillow 11.3 ships 105 different binary wheels. That's 105 different binary configurations that need to be configured, built, and tested. So how do you generate a release with 105 different binary artifacts? Well, this is where a tool called cibuildwheel comes to the rescue. cibuildwheel provides the tooling to help you build a wheel in CI. For the uninitiated, CI is continuous integration. Think GitHub Actions. Despite the name, it's actually not CI specific. You can also install and use it locally, but obviously it does work really well as part of a CI pipeline, generating 105 binary artifacts as part of a release. cibuildwheel provides the tools to configure the matrix of options as a matrix. To make your package compatible with cibuildwheel, you need to start with a package that is compliant with PEP 517 and 518. That means you need a pyproject.toml file, and that file declares a build system table with a requires field and a build backend field. Requires defines the set of tools that must be in your environment to be able to build a wheel for your package. Build backend specifies the path of a module that will be installed by the requires. That module has to adhere to a specific interface, which provides an entry point to trigger a build. The build system table defines the interface that Python will use to build a wheel for your Python code. It does not care how that happens, only that the build backend will define the entry point. In practice, you'll likely need a bunch of other configuration details, PEP 621 and 639 project configurations. You'll likely also need to provide configuration that's needed by your chosen PEP 517 build backend. There are a whole lot of PEP 517 compliant build backends. Setup tools, Hatch, Flit, Poetry, Maturin, Meson. Which one should you use? That's entirely up to you. From Python's perspective, it does not matter. And that is the point of PEP 517. But once a project adheres to those PEPs, cibuildwheel can then do its magic. You don't need any additional configuration to use cibuildwheel. Pip install cibuildwheel, then run cibuildwheel. And by default, cibuildwheel will run through every currently supported Python version for your current platform and use the PEP 517 interface to build a wheel for each currently supported Python version. At present, that's at least 6 wheels, one each for Python 3.10, 3.11, 3.12, 3.13, 3.14, and one for 3.14 free-threaded. On macOS, you have to have the official CPython interpreter for each Python version installed. If those interpreters aren't available, you get an error during the build process. On Linux, you need to have Docker installed. The many Linux and Muscle Linux Docker images are then used to host the builds. On Windows, cibuildwheel will automatically download and cache Python interpreters with Nugget as they're needed. Just call cibuildwheel is the simplest possible invocation of cibuildwheel, but cibuildwheel is also very configurable. You can configure cibuildwheel to skip certain Python versions if you want, or to include PyPy builds, or to skip and include specific architectures. And there are then multiple ways to define those configurations. As an example, macOS currently supports both x86-64 and ARM64 architectures, and there is a universal 2 tag that supports both. All 3 options can be compiled from a single build machine. By default, cibuildwheel will only build the current architecture, but you can configure cibuildwheel to build all the options. From the command line, pass in --arches all, and on a Mac, cibuildwheel will generate 18 wheels, 6 for x86-64, 6 for ARM64, and 6 that are universal 2. You can also specify options in your pyproject.toml file. If you add a tool.cibuildwheel section, you can specify the architectures that you want to build by default. So, for example, here, you're building all available architectures on every platform. Those configurations can also be platform-specific by adding subtables for each platform. So in the second configuration, we're saying we want to build all architectures on macOS, but only the AMD 64 architectures on Windows. Alternatively, you can configure cibuildwheel with environment variables. If you define cibw arches, that value will be handled the same as if it had been passed in as a command line argument, or specified in the configuration file. The environment variable can also be qualified to only apply to specific platforms. So, in a single environment, you can define environment variables for both macOS and Windows. When the build occurs on macOS, the macOS version will be honored. When the build occurs on Windows, the Windows version will be honored. And that's just one example of arches. cibuildwheel has dozens of options for configuring exactly what versions, interpreters, and architectures are built, and every option can then be defined on a platform-specific basis. By default, cibuildwheel will just build the wheels, but any good CI process should also be running the tests. So you can tell cibuildwheel how to run the tests for your project. Test command defines the command line to run the test suite. Test sources defines what subset of the entire source tree is necessary for the tests to run. Test requires defines specific packages that need to be installed to run the tests. Or you can specify test extras to define an optional dependency set, or test groups to use a PEP 735 dependency group definition. And these options can also be defined using environment variables with cibuildwheel test command, for example, or platform-specific environment variables like cibw test command macos. If you set this up and you run cibuildwheel, not only will you get a flood of wheels for each version of the wheel that is built, a clean test environment will be created, the wheel will be installed, and the test suite will be executed. Okay, so now we can pull all the pieces together and actually use cibuildwheel in CI. I'm going to show GitHub Actions here, but the cibuildwheel docs have examples for Azure pipelines, Travis CI, Circle CI, GitLab CI, and Cirrus CI. You set up a workflow that on GitHub Actions runs on a push or a pull request. You add a build wheels job that runs a build matrix that's going to run on Linux, Windows, and macOS. What's in that matrix job? Well, cibuildwheel publishes a GitHub Actions workflow that will do all the heavy lifting of getting cibuildwheel set up to execute. So you only need 3 steps: a checkout, so your code is available, cibuildwheel, and then saving the build artifacts that cibuildwheel generated. That workflow will run the pyproject.toml configuration for all 3 desktop platforms on all stable Python versions, producing dozens of wheels, depending upon what configuration is in your pyproject.toml file. But the configuration doesn't have to be entirely in pyproject.toml. This is why environment variable configuration is useful. pyproject.toml configurations will apply to every user who downloads the project. Environment variable configuration lets you specify this specific release configuration, and do so without the need to add complex branching logic in your workflow. So you set the variables that apply to the platforms that need them, and cibuildwheel will do the rest. Okay. But can't you do all this by yourself? Can't you just set up a CI matrix over operating systems and Python versions to spit out all the wheels that you need by just calling Python-m build by yourself? Well, yes, you probably could. However, that means you're now responsible for a very complex build matrix. cibuildwheel abstracts the complexity of everything past the level of the operating system. And in the case of Linux, that's a non-trivial matrix because you've got many Linux and muscle Linux targets that you need to make sure you've got correct. Using cibuildwheel means you need a top-level operating system matrix, but then cibuildwheel manages everything else, including automatic updates to your matrix. When cibuildwheel 3.1 was released, Python 3.14 and 3.14 free-threaded support was automatically added to every matrix by default. And the only change you needed to make as an end user was to update your pinned cibuildwheel version, which is something that Dependabot would have done automatically. But one of the biggest reasons to use cibuildwheel, are you sure you are building your wheels correctly? cibuildwheel does 2 very important things you probably aren't doing as part of your handcrafted cibuildwheel pipeline. Firstly, tests are run using the built wheel. If you build a wheel and then run tests, it is probable you are not actually using the wheel you built to run your tests. You're using a local source checkout and local build artifacts. And that should be the same, unless it isn't. cibuildwheel does this test isolation for you, so you know the distribution artifact you're uploading to PyPI is actually the thing you're testing. Secondly, every wheel that is produced is also audited and repaired as part of the build process. If you build a wheel on your computer, it is trivial for you to accidentally link in a binary that exists on your computer, but won't necessarily exist on the machine where the wheel is ultimately going to be used. cibuildwheel automatically audits every wheel to make sure this doesn't happen, and if it does, where it can, it repairs and rewrites the library dependencies so that the wheel is guaranteed to be self-contained. Now, both of those things are things you could set up yourself, but in all likelihood, you won't set up those protections until after you've published a wheel that's been broken. With cibuildwheel, you get all those protections for free. It also means that the complexity of setting up and managing cross-platform compilation environments for iOS and Android is handled for you. From the perspective of cibuildwheel, iOS and Android are just another platform. If you've got cibuildwheel configurations that work for desktop, cibuildwheel will likely just work for iOS and Android as well. To build for Android, you need to have the Android SDK installed with the Android home environment variable set, This can be either a full Android Studio install or just the command line tools. You need to have a Java SDK installed with Java Home defined, or at least Java C on your path. You need curl installed to manage some downloads, and you need PatchElf installed to perform some of the post-build auditing and fixes. Any Android-specific build details can then be configured with the tool.cibuildwheel.android table in your PyProject.toml, or with the _Android suffix on any cibw environment variable. There are 2 architectures that are supported, x86-64 and ARM64 V8A. 32-bit Android is not supported because it's not a Tier 3 supported platform in CPython itself. You can build Android wheels for both architectures on any Windows, Linux, or macOS machine, but only the local architecture will actually be tested. So if you're on an x86 Windows machine, only the x86 wheel will actually be tested through the simulator. To build for iOS, you need to have Xcode installed, and you also need to install the iOS SDK add-on inside that. iOS-specific build details are configured with tool.cibuildwheel.ios table in your PyProject.toml, or with the iOS suffix on any CIBW environment variable. There are 3 architectures you need to worry about with iOS: x86-64 iPhone Simulator, ARM64 iPhone Simulator, and ARM64 iPhone OS. iPhone Simulator and iPhone device binaries are not ABI compatible. They are separate targets producing separate and incompatible wheels, even if they're running on the same CPU architecture. You can only build iOS wheels on macOS because you need Xcode, and only, again, the simulator wheel will be tested. As with Android, only the architecture that matches your native architecture will be tested. So on an x86 simulator, if you're on an older laptop, an ARM64 simulator on newer machines. The complexity of architectures on mobile platforms means there's sometimes a need for architecture-specific configuration. cibuildwheel can do that. Using the overrides configuration syntax. Overrides lets you define a pattern of build targets that match and then replace or augment settings when that pattern matches. So, for example, you could specify, as we have here, that when targeting any iOS simulator, the build should redefine path in the build environment. Or, when targeting any iOS ARM64 platform, append an extra requirement to the test requirements. Now, although these are iOS examples here, the override syntax actually works everywhere. So you could use it on Windows, on Android, wherever you need it. Some extra details to keep in mind when configuring tests for mobile platforms. First, test command must be a Python entry point. Essentially, must start with Python -m. Android will also allow Python -c as an entry point. On desktop, test command can be a shell script or any other command line you might want to invoke. That won't work on mobile because you don't have a shell environment. Android and iOS code is tested using a testbed app, an iOS or Android application whose sole purpose is run the test suite. CPython includes a testbed project for both iOS and Android, and cibuildwheel will manage the process of cloning that testbed so you can run your test suite as a specific artifact. You also must define test sources, even if it's empty. Why is this? Well, at runtime, the testbed app is running on the iPhone simulator or on the Android simulator, and it won't have access to your local code checkout. So you need to specify what is going to be copied into the testbed to be used at runtime. On iOS, you also must define xbuild tools, again, even if it's empty. Xbuild tools specifies native local tools like CMake or Ninja that you want to be available in the cross-platform build environment. The wheels that are generated will specify their OS version compatibility. If you want to set a different version, you can export the iPhone OS deployment version or Android API version, API level environment variables. Once you're configured, call cibuildwheel, pass in the platform you want to build for, -- platform iOS, -- platform Android, and cibuildwheel will create isolated cross-platform build environments, invoke a cross-platform build of your wheel, set up a testbed application, copy your wheel into the testbed, copy your test code and test requirements into that testbed, compile the testbed, start a simulator, run the testbed, and rinse and repeat for every supported Python version. CI configurations that support mobile need to be a little bit more complicated because you actually need to differentiate between the build platform and the target platform. To do that, you either need to define more entries in the build matrix and configure that matrix so there is one build on macOS to build for macOS and one build on macOS to build for iOS, and so on. Or you can split out individual architectures as matrix targets. Alternatively, you can specify a separate workflow for your mobile, iOS, and Android wheels. That keeps your desktop matrix relatively simple, but at the cost of repeating some of your CI configuration. What platforms can you use to run tests? Well, as of right now, you can run the iOS tests on any macOS CI environment. Unfortunately, any day now, GitHub is going to start deprecating macOS 13 runners, which is the last GitHub configurations that run on x86-64. So that'll lose your ability to test x86-64 wheels. As for Android, the problem is that CI environments are essentially containerized environments, and the Android emulator doesn't like running in containerized environments. At present, the GitHub Actions on Linux is the only CI platform that we know of that supports running the Android emulator, and even there you have to do some preparation steps to enable KVM virtualization. That step shouldn't be necessary once Python 3.14 final is out, but at least for now you have to add a couple of extra configuration lines for Android. Details are in the CI build wheel docs. What do you need to do to a package to make it compatible with Python platforms? Well, the good news is that most Python code, and that includes any Py3 none any wheel, will just work. Python is ultimately a write once, run anywhere language, and for the most part, that holds. The only place it falls apart is when you start to do things that are platform specific. In code, the first thing to look out for is any references to sys.platform or os.name or platform.system. If you've got code that is making decisions based upon platform, you're going to need to add logic branches to accommodate iOS and Android as possible responses from sys.platform and platform.system. The other big thing to watch out for is use of subprocess, multiprocessing, and any other API that creates a subprocess, like os.spawn and os.fork. iOS and Android don't do symmetric multiprocessing. Essentially, the app that is in the foreground is the only app that is running at any given point in time. So you can't call subprocess to do something in the background or offload work to other CPUs by using multiprocessing. If your package does that, you'll either need to disable that functionality or find a different way to do that task, such as using threads instead of using processors. And those caveats also apply to your test suite. If you've got tests that create subprocessors, those tests won't work on mobile. If you need to, you may need to add additional platform-based skips to your test suite to move around tests that are trying to do subprocess-based activity, and so on. But my experience has been that the Python code is not the hard part of porting a package to mobile. The hard part is the non-Python code and the builds of that code. The benefit of PEP 5.17 is that Python doesn't have to care how to build your package. It just calls the PEP 5.17 interface. The downside is that package maintainers do need to care. Whatever tool you're using to build your package needs to be able to target iOS and Android. Setup Tools has good support for iOS and Android. The Python environment that is used to run builds has been patched so that it pretends to be the target platform, so it's relatively straightforward to add extra code branches to add support for mobile platforms. CPython even provides shims to make it easier to configure iOS compilers using naming schemes that match the expectations of a lot of Unix tooling. But in addition to configuring the build of your package, you also need to ensure that any binary dependencies are available. For example, Pillow is a Python package. It's configured using Setup Tools. That build almost worked out of the box. But Pillow also uses libpng and libtiff and freetype, which are all non-Python binary dependencies, and they all need to be compiled for each iOS and Android architecture. And in addition, when building for iOS, the dependencies or the dependency libraries need to be static. This is an unfortunate side effect of how iOS loads libraries. The compilation, or the complication is that these dependencies might use configure, and they might use CMake, they might use a custom Perl script to manage their builds. If it's a configure-based project, you can usually pass in --host and --build to configure for the platform you want to build for and the platform that you're building on. Note that you have to use the GNU preferred AArch64 format for describing the ARM64 architecture, because GNU. You can use AArch64 Apple iOS for both the device and the simulator, as long as the rest of your path configurations are correct. If you do need to differentiate the simulator, AArch64 Apple iOS simulator is the Apple specified tag, but config.sub doesn't recognize that as a valid option, despite me submitting the patch multiple times over the last 2 years. So you may need to patch config.sub. You may also be able to use --disable shared and or --enable static to force a static-only build. CMake has native iOS support, but it doesn't do a great job of differentiating device and simulator, and it seems to expect the use of Xcode projects a lot of the time. I found the best approach is to lean on macOS configurations, but pointing at the iOS version numbers and system roots. You can use xcrun to get you that system root. Meson is a cross-compilation environment based upon parsing a cross file. You pass that in as an argument, and the values that are provided in the cross file will be used instead of any automatically detected platform values. If your dependency doesn't use configure, CMake, or Meson, good luck, have fun. It very much depends. The biggest gotcha when building third-party libraries, compilers are really good at identifying CPU architectures. They are not good at identifying platforms. If you are trying to build an iOS binary wheel and you have a macOS ARM64 version of a library on your path and you try to build the iOS library, it's really easy to accidentally include the macOS version of the library in your iOS wheel. For this reason, cibuildwheel explicitly clears your path during builds to only include paths that are known to be appropriate for iOS. So you may need to configure cibuildwheel to explicitly reallow certain paths if you've got local binaries for iOS in some location. All right, so you've built your wheels, you've published them to PyPI. How do you use them? Well, pip allows you to just install iOS and Android wheels. Pass in -- platform. You can specify the wheel tag that you want to satisfy with your downloads. That will put iOS-compatible wheels into whatever virtual environment you're currently using, which will be a local macOS environment. So you might want to specify -- target to specify an output directory, so only iOS content is in that directory. Also, at the moment, at least, -- platform isn't transitive. If you install an iOS version of my package, and my package needs to install other binary requirements, pip will unfortunately install the macOS version of those downstream requirements. So you may need to use -- nodeps to prevent that dependency chaining from happening. If you're a UV user, well, support literally landed last week for iOS and Android as platform tags. Consult your UV documentation for details. Or if you're a briefcase user, just add the package to your apps requires and you're done. All that stuff is managed for you. What's next when it comes to packaging, and mobile packaging in particular? Well, one big issue we haven't tackled yet are Python packages that are built using Rust. Rust is a compiler toolchain unto itself, and it has support for iOS and Android, but we need to work out what modifications to the Rust PEP 517 build backends, like Maturin and Setup Tools Rust, are required to support those platforms. We're also going to be looking at ways to consolidate and standardize the way that cross-platform builds actually work. Cross-platform builds on Android and iOS have very similar constraints, but the cibuildwheel implementations take very slightly different approaches. However, they share enough similarities that there is an opportunity to consolidate those similarities into a shared code base. I've already started working on this with a project called Crossbuild. Crossbuild is a work on progress. I've published Crossbuild in a sort of a pre-alpha state so that I have something to discuss in the coming week at the CPython Core Team Summit in the UK. That might lead to a new PEP enhancing PEP 517 to add cross-platform support. But you can already use Crossbuild to build a virtual environment that can fake being iOS, Android, or Inscripton, and pip install just works in that environment, installing platform or target appropriate platforms, packages, and all their dependencies, including all the transitive issues. So, our call to action. We need your help. Malcolm and I are only 2 people, and there is a limit to how many projects on PyPI we can port if we're the only people doing it. But the tools now exist. You, yes, you, can add support for mobile platforms to the Python packages that you use. If you visit beware.org/mobilewheels, you will see the 360 most popular packages on PyPI by download, categorized as to whether they are mobile ready. Pick a package that's in yellow, see if it uses cibuildwheel. If it does, add an iOS and Android configuration as a pull request. Now, ordinarily, this would be where I say, if you're looking for something to sprint on, this is one way to contribute, and I'll be around to help out. But unfortunately, I won't be here for the sprints because I'm on a plane tomorrow to fly to the UK for the core team sprint. But it's still a great place to contribute. See how you go. If you'd like to know more, the Beware project is a great place to get started with Python on mobile platforms. We've also got a Discord plus discussion forums and ticket trackers for all the projects. Details on the website, beware.org. Or you can go to the cibuildwheel documentation directly. It's part of the resources of the Python Packaging Authority or the PyPA. Thank you all very much.